You may have heard the growing excitement about newly discovered exoplanets as observatories like the James Webb peer out across the Milky Way. We discovered the first planet outside our solar system only a few years ago, in 1992, but since then, over 5,500 have been confirmed in the comparatively limited area of space that we inhabit, only a few thousand light-years across. When the Milky Way spans 105,700 light-years across, the possibility of billions to trillions more throughout the rest of our galaxy is tantalizing. Every star on average has at least one planet, and maybe more. With all of these exoplanets out there just waiting to be discovered, it's natural for us to think about Goldilocks zones and planet habitability. After all, humanity has its sights set on populating the stars, and mathematically speaking, an Earth 2.0 is undoubtedly waiting for us out there. In fact, you may have already heard the phrase Earth 2.0 in the headlines of stories or films claiming the discovery of a new planet suitable for human existence and settlement. But don't believe the hype. All of the planets we've discovered thus far have sucked, to put it mildly. And after hearing what I'm about to tell you, you'll agree that going to any of them is the last thing any rational person would want to do. Hello everyone, welcome back. You're watching Zeey, the Space Fanatics. Join me today as I take you on a big real estate tour of the prospective Earth 2.0s we've identified thus far, and explain why now is not the time to go on the planetary property ladder. It's a good idea to start with your non-negotiables when picking an Earth 2.0, just as when buying a house. Some of this is quite straightforward to consider. Take for example, temperature. You want a nice, temperate environment that is neither too warm nor too hot. Given that temperature decreases as one moves away from the sun, every planetary system has a sweet spot where the temperature of a planet is likely to be just right, not too hot, not too cold, comparable to Goldilocks with her bowls of stolen porridge. As a general rule, if a planet is at the correct distance from a star, it may have an acceptable temperature for humanity to settle. Of course, this isn't a guarantee. After all, Venus, a planet in this zone, should be perfect in principle, but its strangling atmosphere makes it the hottest planet in our solar system, despite its greater distance from the Sun than Mercury. As a result, the atmosphere clearly plays a role in all of this. Speaking of atmosphere, it's something you'll want to look for on Earth 2.0, preferably something with oxygen and water vapor, and nothing that would poison us, but at the very least something that could trap heat and provide some protection from space radiation. However, sometimes a non-negotiable is merely the proximity of neighbors. So consider the first significant reason why the galaxy's exoplanets fall short: their star neighbors. Our star is classified as a G-type yellow dwarf, which is a rather fast-burning, short-lived star when compared to some of the other alternatives out there. Stars like our Sun typically exist for 10 billion years until their cores collapse and they become red giants. It is stable, and that stability has aided the life that has eventually grown here. Yellow dwarfs, on the other hand, are extremely rare in the Milky Way, accounting for only 10% of all stars. Longer-lived red dwarfs, which make up 75% of the stars in our galaxy and can survive for 14 trillion years, longer than our universe has existed, are far more prevalent. Unfortunately for the planets that orbit them, red dwarfs have a slew of downsides. To begin with, red dwarfs have a significantly closer Goldilocks zone than their yellow cousins. They burn less brightly, with luminosities ranging from 10% to a measly 0.0125% of that of our Sun, so unless you want to live on a world shrouded in perpetual night, which sounds cold and depressing to me, and will make growing plants difficult, an Earth 2.0 would need to be much closer to its red dwarf to compensate. This would not be a problem in and of itself if it weren't for the second trait of red dwarfs that makes them highly disagreeable neighbors: their volatility. The main source of our space weather is our Sun. It emits a steady stream of solar winds, flares, and coronal mass ejections. However, this pales in comparison to the quantity of space weather produced by red dwarfs. Red dwarf flares can be 100 to 1,000 times stronger than those generated by our sun. Red dwarfs' regular blasts of plasma and radiation are intense and harmful enough to take away atmospheres and potentially boil liquid water on planets in the habitable zone. Given how much closer planets are to their star in a red dwarf system, the chances of life arising before being struck with a life-sanitizing dose of X-rays are pretty poor. If you wish to live on a planet orbiting a red dwarf, you'll need some serious sunblock. Many exoplanets, including astronomer favorite Kepler 186f, which some scientists hoped might be habitable, are therefore ruled out. While it may be feasible to live in rather difficult conditions in a deep underground bunker on such a planet for a time, the experience would be far from pleasant. However, even when there are no violent solar weather events, planets orbiting red dwarfs have another issue: they are tidally locked. Because the planet is tidally locked, the same side of the planet always faces the star as it revolves. There is no rotation between day and night. One side of the planet is perpetually hot, while the other is perpetually dark. Because of gravitational limits, planets near their sun tend to be tidally locked. Just look at Mercury, which has days that last 176 Earth days, or 2 Mercurian years. This lack of rotation might render most of the world uninhabitable, with blistering, desert-creating heat on one side and freezing ice on the other. Even if humans attempted to live in the small band of twilight that would encircle a tidally locked planet, liquid water would be difficult to come by, since any moisture in the air that made its way to the night side of the planet would become trapped and formed as ice. Overall, the planet would be very dry, with no rain even in the twilight zone. Not to mention the low strength of a magnetic field that would be present on a tidally locked planet. The Coriolis effect, the rotation of the Earth giving momentum to rising and descending liquid metal in its core, is hypothesized to influence the dynamo effect that produces the magnetic field on Earth. Such a magnetic field would necessarily be weaker without this rotation. So I'm afraid to announce that worlds like Proxima Centauri b, our nearest exoplanet, is out. Proxima Centauri b is otherwise an intriguing contender. Its proximity makes it one of the simplest planets for humans to reach, given it is only 4.2 light-years away. It's supposed to be a rocky, Earth-like planet, which is convenient because living on a gas giant could be difficult for anyone who likes solid floors beneath their feet. Most intriguingly, its mass and radius are quite similar to Earth's, implying that it possesses a similar gravity. What is the significance of this? Let's compare it to Kepler 452b, another Earth 2.0 possibility. The first planet to be given that name, and the planet characterized as the closest twin to Earth by a NASA expert. Kepler 452b has a lot going for it. It is orbiting a yellow dwarf at a similar distance to us. This suggests it's in the Goldilocks zone, where liquid water can exist on the surface. However, it is a super-Earth. This indicates that it has a mass and radius combination that causes its gravity to be around twice that of Earth. How much is too much when it comes to gravity? According to some researchers, the amount is 4 times Earth's gravity, which is around the maximum of what a human can withstand. However, even living in twice the gravity of Earth could be uncomfortable. To fully visualize this, or at least get a rough idea of it, imagine lying down, but then imagine another person lying down on top of you, placing all of their weight on you. Every night this is your night. Every breath is being fought for. Come morning, you must pick up that extra person, haul them onto your back, and then carry them everywhere you go. Everywhere. And be careful not to tumble, as breaking a bone is more easier when it happens abruptly. Falling down the stairs is no longer uncomfortable, it is almost certainly fatal. This is something that everyone must do. Elderly people, the sick, small infants attempting their first, wobbly step. With this in mind, it's simple to imagine how tiresome life in double gravity could be. If you're a bodybuilder or athlete, you should be fine. For most people on Earth, however, it would be a slow agony. Your heart is racing so fast to move your blood that you feel like you're running even when you're not. And how about double the gravity? Add another person on top of that. And it doesn't get much better going the other way. Sure, once that weight is lifted, everything becomes much easier. However, living in zero gravity poses a number of health hazards, as evidenced by astronauts who have just spent a few months on the International Space Station. Calcium leaks out of your bones over time, causing them to become brittle. Your muscles shrink. Your heart is having problems. Your immune system suffers as a result. Overall, even if you exercise every day, your long-term prospects in a low-gravity environment aren't looking good. A fact that NASA scientists are grappling with as they try to figure out how to set up human outposts on places like the Moon or Mars, where astronauts might go to live for only a few years. Humans have spent millions of years acclimating to life on Earth. We're used to the way things are around here. We're simply not adapted to living somewhere else. We haven't developed to deal with such situations. It's a credit to how successfully we've adapted to our birth environment in some ways, but it's a significant barrier if we ever wish to live somewhere else. So the search for Earth 2.0 continues. As previously stated, there are most certainly billions of unknown planets in our Milky Way galaxy. The chances of there being at least one being out there that meets our gravity, temperature, lack of life-threatening radiation and presence of atmosphere and water are high enough to be assured. Finding one that satisfies the criterion is a more difficult task, especially as most planets are still invisible to even the most powerful telescopes, save for a brief moment when they pass in front of a convenient star and block out its light. If someone claims to have discovered Earth 2.0, I'd take it with a grain of salt. We won't truly know if a planet is suited for human life until we transcend the chasm of space and get there to see it for ourselves. Of course, until we figure out how to do that, it's all a bit of a moot point. Alright, that is all for this video. Thanks for watching, everyone. Is there anything you like to say? Please tell us in the comments below, and don't forget to subscribe and ring the bell so you don't miss any of our daily videos.